18 PCH 180151 Unit 3 Magnetochemistry. Today we are going to discuss antiferromagnetism and ferromagnetism. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Let's begin with introduction. We already discussed the anomalous magnetic moment of magnetically dilute transition metal complexes. Assuming that the magnetic property of a metal ion is influenced only by the ligand field. An anomalous magnetic moment may also arise in a magnetically concentrated complex. As already noted, the magnetic exchange interaction in such a complex occurs when the neighboring magnetic centers are close enough for direct or indirect orbital overlap. This interaction affects the magnetic property of the complex and sometimes swamps the ligand field effect. In fact, almost all paramagnetic compounds are involved in exchange interaction to a certain extent, and this interaction is dominant only at a very low temperature. When the exchange interaction energy is greater than kappa T, the result is the cooperative phenomena of ferromagnetism or antiferromagnetism. Already we have discussed the plot of 1 by xi versus T, where when we decrease the temperature at Curie point of temperature, the magnetic susceptibility value drastically increase and the substance behavior would be ferromagnetic, and at nil temperature the magnetic susceptibility value drastically decrease and the substance behave antiferromagnetically. The magnetic moment of a complex involved in an exchange interaction may be more than or less than that of a complex not involved in an exchange interaction. The former situation is a characteristic of a ferromagnetic body, whereas the latter is a feature of antiferromagnetic substance. That features represent antiferromagnetism of that substance. In an antiferromagnet, the neighboring magnetic centers are opposed to each other. That means anti-parallel arrangement of the spin. But in a ferromagnet, they are aligned parallel, like this parallel spin of electron gives antiferromagnetic behavior, and anti-parallel arrangement shows antiferromagnetism. Although ferromagnetism is rarely encountered, it is a much more useful phenomena than antiferromagnetism. Now, types of antiferromagnetism. There are two types of antiferromagnetism, namely, number one, intramolecular antiferromagnetism and intermolecular antiferromagnetism. We're going to discuss both with examples. First one, intramolecular antiferromagnetism. Intra means within single molecule, internally it going to indicate antiferromagnetic behavior. This arises when the interacting paramagnetic centers are stationed within the same molecule. As already I have said, within the molecule the arrangement is such that it's going to behave as antiferromagnetic material. Necessarily, the compound like dimeric arrangement or polymeric arrangement, they are having intramolecular antiferromagnetic behavior. The commonest example of this class is the copper 2 acetate monohydrate dimer, that is Cu2CS3COO4.2H2O, that is 2 molecule of copper 2 acetate monohydrate behaves as if it is intramolecular antiferromagnetic substance. The complex K for Ru2OCl10, as for example K for Cl5Ru-O-RuCl5. The oxygen here act as a bridged atom between these two complexes. So it's a bridged complex, also belong to this intramolecular antiferromagnetic class. A monometallic low spin D for rubidium 4 complex is expected to exhibit two unpaired spins. But the complex K for Ru2OCl10 is dimagnetic. All the electrons get paired up when this bridged formation take place. And due to the coupling of the neighboring spin, leading to this antiferromagnetic exchange. Suppose we are going to talk about a single complex of D4Ru4. It is expected to have unpaired spin and behave paramagnetically. But when the bridged complex K4Ru2COCl10 is obtained, it is dimagnetic because both the unpaired electron mutually paired up gives dimagnetic behavior, and due to that coupling of a neighboring spin leading to the antiferromagnetic exchange. For copper 2 acetate monohydrate, the room temperature magnetic moment per copper 2 ion is 1.4 Bohr magnetron, whereas no interaction predicts magnetic moment greater than spin moment, and that value is equal to 1.73 Bohr magnetron. In the D1 molybdenum 5 complex of ethyl xanthate, the neighboring spins are completely neutralized due to the antiferromagnetic exchange, making the complex dimagnetic. Here is the example of molybdenum 5 complex, and that is a D1 molybdenum 5 complex of ethyl xanthate, and in this complex the neighboring spin are completely neutralized due to antiferromagnetic exchange. Such comparison we have studied in the previous example. Here in this bridged complex we found the same single unpaired electron coupled with each other, and it leads to antiferromagnetic behavior. Similarly, in this complex, the bridged oxygen between these two molybdenum will going to couple the unpaired electron, and dimagnetic behavior is going to be observed, and it behave like anti-magnetic and intramolecular antiferromagnetism is going to be observed in this complex. If there were no interaction between the neighboring spins, the result would have been magnetic moment minus mu subside s. That value would be 1.73 Bohr magnetron. Second is the intermolecular antiferromagnetism. Here intermolecular means two same kind of molecule, but molecules are different. Same category of molecule but two different molecules, and the previous case a single molecule. Here two different molecule is there. Here the secondary magnetic interaction take place over essentially the entire crystalline lattice. The transition metal oxides and halides belong to this class. As for example, KMF3, where M stands for almost any bivalent transition metal ion over here. So the fluoride complex, potassium fluoride complex of any transition bivalent transition metal ion will going to demonstrate intermolecular antiferromagnetism. A weak intermolecular antiferromagnetism occurs in many transition metal complexes. The extent of such an effect may be checked by measuring the magnetic susceptibility in solution, where it should be poorer than in the solid crystalline state. Antiferromagnetic exchange pathways. The spin-spin interaction giving a low magnetic moment may take place through one or two processes, namely direct metal-metal interaction via the overlap of subtable metal orbitals and super exchange arising from the paramagnetic spin density from one metal ion through the orbital overlap of the diamagnetic bridging atoms to an adjacent metal ion. The superexchange phenomena thus usually involves three atoms, while direct metal-metal interaction is between two metal. There is no intermediate element, while in superexchange there should be third bridged atom. So bridging atom is required for superexchange phenomena. That is its speciality or limitation, you may say. It may be worthwhile to point out that in most coordination complexes, the shell of the ligands surrounding the metal ion is such that a long metal-metal distance is usually maintained. This prevents the magnetic dipole of the metal ions from influencing one another, thus ensuring a magnetically dilute system. In a magnetically concentrated system, the metal-metal distance is either short enough for direct interaction or the bridging ligand atoms successfully transmit the interaction between the magnetic dipoles. Now let's take first example, that is direct metal-metal interaction. In order for the direct metal-metal interaction to occur, the structure of a complex should be such that there is a scope for an overlap of the metal orbitals carrying unpaired spins of electron. A common example to illustrate this mechanism is copper 2 acetate monohydrate, which in reality is a dimer both in the solid state as well as in a solution state or liquid state. The two copper atoms in this complex are 2.64 angstrom apart. That is a distance between two copper-copper metallic element, that is 2.65 angstrom. These two copper atoms are bridged by four acetate groups with two water molecules coordinating along the copper-copper axis. We can see in this figure. Here you can see that these two copper, the distance between these two is 2.65 angstrom, and these two acetate ligands are bridged between these two copper and two water molecule axially arranged. So this is metal d orbital and it has this kind of interactions when we put in a Cartesian system, and it's going to generate a delta bond. Such a structure allows a lateral overlap of the dx square minus y square orbital of each of the two copper 2 ions, thus generating a delta bond, theta bond. The d orbital electron distribution and the energy order of the d orbitals in this complex is arranged in this way. dxy antiparallel arrangement is lower than dxz, have antiparallel arrangement which is nearly equivalent to dy/z antiparallel arrangement, which is less than dz square antiparallel arrangement, and which is less than dx square minus y square. So you can see that the higher energy, that is of higher distribution of electron or energy order, we have high energy in dx square minus y square. The unpaired electron resides in this x square minus y square orbital, that is in 2b1 state. It should be noted that the alternative view, namely the antiferromagnetic interaction, actually take place via super exchange through the bridging acetate groups, which we have seen in the figure before, is gaining ground. For instance, in copper 2 complexes with some substituted acetate groups, the copper-copper distance is largely 2.69 angstrom than in the simple aceto complex, and yet the exchange coupling constant J get increases. A slight different situation exists in the N-hydroxyphenyl salicylidene iminato oxovanadium 4 complexes having subnormal magnetic moments. The d1 electron is located in the ground state orbital dxy, and the energy order of the d orbital in this complex is represented as dxy have one unpaired electron, which is lower energetic, and dxz is having higher energy than dxy, equivalent energy, that is dyz, which is lower than that of dx square minus y square, which is lower than that of dz square. So unpaired electron would be in the lower energy, that is dxy. The oxygen atom of the tridentate dibasic skip base act as a bridges between the two oxovanadium 4 ions. Since it is the dx square minus y square orbital which faces the bridging oxygen atoms, and since this orbital does not carry the unpaired spin, the spin-spin interaction cannot occur via super exchange in this complex. The complex, that is N-hydroxyphenyl salicylidene iminato oxovanadium 4 complexes. Direct metal-metal interaction is there, although it has a bridging ligand, but since it is the dx square minus y square orbital which faces the bridging oxygen atom and orbital does not carry unpaired spin, the spin-spin interaction cannot occur via super exchange in this complex of vanadium 4. Indeed, a dimeric formulation brings the two dxy orbitals, that is having the unpaired electron, of the two oxovanadium 4 ions so close to each other that the spin-spin interaction may proceed via the sigma overlap of these two orbitals, and that make them coupled and gives antiferromagnetic behavior through direct metal-metal interaction. The indirect pi pathway of super exchange through the dx square minus y square to pz oxygen to dx square minus y square of vanadium overlap is expected to be weak, since the dxy to dx square minus y square mixing will only occur in the high energy state. Molybdenum 5 is a 4d1 system, and in oxomolybdenum 5 the d orbital ordering is comparable to that in the oxovanadium 4 complex. The spin-spin coupling in the N-hydroxyphenyl salicylidene iminato and ethyl xanthato complexes of oxymolybdenum 5 occurs through the overlap of the dxy orbital of two adjacent molybdenum 5 ions. Many examples of the dimagnetic ground state via antiferromagnetic metal-metal interactions are found in complexes with the metal ions, a low oxidation state. The complex Mn2CO10 is dimagnetic in nature. The oxidation state of manganese in this complex is 0. That is, Mn0 belongs to the 3d7 system. In this complex, the Mn-Mn distance is about 2.92 angstrom and each manganese is 6 coordinated having D2sp3 hybridization. The inner laying 3d orbitals have 3 paired spins. The 7th electron is housed in one of the 6 hybrid orbitals and the other 5 hybrid orbitals overlap with the carbon monoxide orbitals, CO orbitals containing lone pairs. An overlap of 2 hybrid orbitals of the 2 adjacent manganese in zero oxidation state containing the unpaired electron leads to dimagnetism. A complete coupling of spin is observed in bis diazoaminobenzonato copper 2 complex. In this complex, diazoaminobenzene, that is C6H5NH N double bond N C6H5, that R is C6H5, that is phenyl group in the figure, functions as a bridging bidentate ligand. The ligand aryl azooxime, that is C6H5N double bond N CR double bond NOH, also react with the copper 2 to give the dimagnetic bis aryl azooxymato complex 2 compound, which is dimeric and serve as a further example of the S is equal to 0 S double bond O ground state. So here you can see that copper and these ligands diazoaminobenzene act as a bridging ligand and gives direct metal-metal interaction. Now next is this super exchange interaction. The indirect 3-atom exchange mechanism. This is the another name of super exchange mechanism. Indirect mechanism, indirect 3-atom exchange mechanism and super exchange all are similar. Affords a suitable pathway for an antiferromagnetic interaction only when there is a joint overlap of suitable partially filled orbitals of 2 metal ions with a filled orbitals of a ligand. The joint overlap may be of the type either sigma and or either of pi. If we take a linear metal-oxygen metal unit, both sigma and pi interaction may occur considering the z-axis and assuming that each metal ion M has one unpaired electron in its dz square orbital and that the filled ligand orbital in pz. We have a situation which we can see in the figure 1 in next slide, and the ligand px orbital will then be a pi orbital and will overlap with the xz orbital of the 2 metal ions, as we can see in next figure B. Since the metal ions have incompletely filled d orbital, one of these electrons from the filled ligand p orbitals may move into the orbital of one of the metal ions. You can see this sigma overlap between the dz square of 2 metal and pz of oxygen, and here in the pi overlap we have dx square minus y square of the metal, dz square xz of the metal and px of the oxygen. So these two overlap we can see here, metal oxygen metal unit figure A and dz xz orbital of metal with px orbital of oxygen, that is in figure B. So these two 3-atom system, the super exchange take place in the complex. If this is so, the ligand electron spin has to be opposite to that of the electron in the metal orbital. A similar situation prevails in the remaining ligand electron and the electron in the second metal ion orbital. This is typological mistake, is a metal ion orbital. Thus, a model for spin neutralization exists. It may be pointed out that we can use for overlap suitably hybridized orbitals of the metal ion and of the ligand donor atom. For example, the species oxygen, bridged oxygen, may be thought of as using two sp hybrid orbitals. The superexchange interaction via metal ligand metal, whether the ligand may be oxygen or fluoride, pathway has been extensively studied in fluorocomplexes of the type M1, M2, F3 and M12, M2, F4, where M1 stands for potassium, rubidium, thallium, and M2 stands for manganese, cobalt, or nickel. An interesting observation in these complexes is that the exchange integral J varies inversely as R the separation of the two metal ions. Thus, the superexchange interaction is highly sensitive to the metal-metal distance. Many copper-2 skip base complexes with subnormal magnetic moments are believed to have a dimeric structure of the type shown in the next figure. These complexes, it is possible perhaps by raising copper-2 from the basal plane to have a pi overlap of the dx square minus y square orbitals housing the unpaired electron and pz orbitals of the bridging oxygen atom. That you can see here, two copper and these two bridging oxygen, and that way the x square minus y square having housing unpaired electron, and that going to overlap with pz orbital of the bridging oxygen to give antiferromagnetic behavior. The likely results of the superexchange interaction at 90 degree and 180 degree between the high spin metal ions in the octahedral symmetry is listed in this table. D1 to D9, 1, 1, 2, 2, D3, 3, 4, 4, 5, 6, 7, 8 and 9 have ferromagnetic behavior. So you can see lower field d orbitals will going to demonstrate ferromagnetic. In D3 you found ferromagnetic, antiferromagnetic both behavior. D4 is uncertain. D5, 6, 7 uncertain for 90 degree exchange, and for 80 degree exchange they demonstrate antiferromagnetism. High end metal complexes D5 to 7 demonstrate antiferromagnetism at 180 degree exchange, and highest higher and transition metals, as that is D8, D9 at 90 degree indicate both the behavior ferromagnetic and antiferromagnetic, and at 90 degree exchange D9 demonstrate ferromagnetic behavior, while 180 degree there is no antiferromagnetism found in D9 case, that is of zinc or copper 1. The figure depicts the 90 degree exchange pathway resulting from the overlap of p sigma orbital of the ligand atoms, the orthogonal dz square orbitals of the interacting metal atom labeled 1, and the orthogonal dz square orbital of another metal atom that is labeled 2. This interaction leads to ferromagnetism. Here you can see that ferromagnetism is observed at 90 degree super exchange pathway dz square p sigma to dz square overlap. The interaction through the overlap of p sigma orbital of the orthogonal dz square orbital and the non-orthogonal T2G set will going to demonstrate antiferromagnetic behavior. Let us consider a D3 system, namely chromium plus 3. The 90 degree super exchange pathway in chromium plus 3. Chromium plus 3 is, we can see in this figure, chromium plus 3 and p sigma. So this interaction will going to demonstrate ferromagnetic coupling at 90 degree super exchange pathway. Let now one p electron or p sigma of the ligand bridging atom be transferred to the vacant dz square orbital of chromium labeled 1. The alignment of this electron in the Eg set will be influenced by its exchange interaction with the electrons in the T2G set. The result is the parallel alignment of this electron with the T2G electrons and consequently the other p sigma interaction, that is denoted as p dash sigma, will be anti-parallel. Further, due to the non-availability of the electron in the Eg set of the chromium label 2, the p dash sigma electron undergoes an exchange interaction with the T2G electrons of the chromium label 2. The consequent antiparallel alignment of the p dash sigma and T2G electron will lead to the antiferromagnetic exchange where J value is negative between these electrons, resulting in ferromagnetic chromium plus 3 chromium plus T exchange interaction. In the oxo-bridged complex NS35CrO-CrNS35Br4, the chromium oxygen chromium link is linear, and in the hydroxo-bridged complex NS35CrOH-CrNS35Br5, the chromium hydroxide chromium link has chromium oxygen chromium bond angle of 120 degree. Here chromium oxygen chromium of oxo bridge, and here oxygen is of hydroxide bridge. So this one is linear, that means bond angle 180 degree. Here this one is having 120 degree. This means that the oxygen is likely to use the sp hybrid orbitals and the hydroxo-oxygen the sp2 hybrid orbitals. Since chromium 3 is a D3 system and both the chromium ions in each of the aforementioned dimetallic complexes are pseudo-octahedral, we may say or assume that the D2sp3 hybrid orbitals are in action. The dxy, dxz and dyz orbitals do not take part in sigma bonding with the ligands. The pz orbital of oxygen is utilized in the sp hybridization, that is of oxo bridge. Then the filled px and py orbital of oxo-oxygen will be available for a pi interaction with the dxz and dyz orbital of each chromium, which undoubtedly carry 2 of the 3 electrons of each chromium 3 metal ion. In the hydroxo complex, only one oxygen p orbital is available for such a interaction. Thus, expectedly, the superexchange interaction will be more effective in the oxo complex than in the hydroxo complex. Thank you for paying attention to this video lecture, and keep asking questions, because as you know that asking question is a beautiful way to gain knowledge. Thank you. This much is enough from my end.